Hello and welcome back again. Happy New Year to all of you, to our lecture course on the very early universe. And I remind you the lecture course consists of two main parts. The first is about a homogeneous universe where we neglect inhomogeneities. And the second part is about inhomogeneities, actually small inhomogeneities on the background of a homogeneous space-time. Now, before the Christmas break, we finished the homogeneous part. Recall we had at the end discussed inflation as a speculative but well-founded speculation of the very early universe, which can solve some of the problems of the old model, flatness problem, horizon problem, but, and this is the most important thing, it can serve as a causal mechanism for structure formation. Yeah, so out of the eventually quantum fluctuations, you will learn that here, we will see that they will evolve into classical perturbations that can serve as the seeds of galaxies. But this will take us first some steps, and I will give you the background here of what is needed for understanding inhomogeneous universe, and I will start actually with gravitational instability in Newtonian theory. Yeah, so it's not because I'm maybe pedantic and want to explain also Newton. It's also a good prerequisite for what will come then in Einstein's theory, because many of the results here you will find, of course, as in corresponding limits of Einstein's theory, and also many of the concepts can already explained here. So it's important, in my opinion, to understand gravitational instability in Newtonian theory. This is what we do today. So in the chapters 4 and 5, I will mainly follow the book by Mukhanov, which is cited on our website, although I will make some changes and some extensions. But for details of the calculations, I mean, my time here is limited, so I cannot give you all the algebraic derivations. For the details of the calculations, I refer to Mukhanov's book or some of the other books that I mentioned on the website. Of course, the general question here is, how fast do small perturbations grow in an expanding universe, right? If you have, say, if you assume the universe is mainly homogeneous and isotropic, as observations indicate, then of course we have some inhomogeneities, some more small perturbations, and out of which galaxies, clusters of galaxies grow. And in order to have a quantitative picture of cosmology, we have to know how fast do they grow. So that's the question. So how fast do perturbations grow in an expanding universe? That's eventually what we want to discuss in general relativity, and first in Newtonian theory. Even before, you will see we will discuss it in the static case. But let's wait here. We make the approximation of an ideal fluid. So we will not discuss here viscosities and other things. And actually, in cosmology, this is valid most of the time. So it's not really a strict limitation here. And this ideal fluid is characterized by some functions. And these are the well-known functions, you know, also from hydrodynamics. So there's the energy density, rho of x and t. Yeah, in Newtonian theory, we only have a mass density. So of course, in Einstein theory, we can either have energy or mass density, and you know, E is mc squared. But here in Newtonian theory, we talk about mass density. Yeah, that's the typical concept in Newton's theory. So then we have the function S, which we call the entropy density per unit mass. And of course we have that fluid moves and it's characterized by a velocity field. And so that's here then a vectorial function v of x and t, and this is the velocity field. And finally we have the pressure P, and the pressure is somehow given by an equation of state. So we assume we have here a function P of rho and perhaps of the entropy density. So this is the pressure, and we call that an equation of state. Of course you know that. That's equation of state. Now, there are equations among them, and these are the famous equations of hydrodynamics that you can read in your favorite books. I mean, Landau-Lifshitz Volume 6 is a very good reference still, if you like to have a smooth introduction into hydrodynamics. And the equations are as follows. Of course, we have the continuity equation that mainly focuses on rho, and we have the Euler equations mainly focuses on V, and we in addition have, because we have an ideal fluid, the entropy conservation. So we don't include here the generation of entropy, as of course you have in nature, but say for this approximation it's not needed, and the Poisson equation that brings in gravity, because the Poisson equation relates the gravitational potential to the density. So step by step, so we first have the continuity equations. Continuity equation. Which is d rho over dt plus nabla rho v equal to 0. Yeah, and you know that also from other contexts like charge conservation. But here it's just a continuity equation. So what goes out of some volume must go through the surface of that volume. Then, very important, the Euler equation from the 18th century, and it gives an equation for the velocity. So the time dependence of this velocity, and then of course you also have the space dependence, and so here you have this derivative where you project the nabla along the velocity, applying on v. Then of course there's something with pressure, it has nabla p over rho, and you have then a term describing the external forces. Now this can be of course many different forces, but here only gravity is of relevant. Also if you have standard hydrodynamics, they are in a gravitational field. So what you have here is then nabla of the Newtonian gravitational potential equals 0. So that's what here brings gravity in. So that's the gravitational potential. We had it very early in relativity 1. For example, if you have spherical symmetry, that's this well-known minus gm over r, but of course in general we don't have spherical symmetry, so it's a more complicated. Then here the entropy conservation. Yeah, which is we have here for the ideal fluid. Of course, if you have viscosity, then you no longer have this, and this means that the total derivative of s over dt is 0. So this depends here on x of t along the flow lines of the fluid particles and t, which consists of two terms. The partial derivative with respect to t, and the derivative here with respect to this part, which is 0. And finally, we have the Poisson equation, which, you know, from relativity class, you have Laplace on phi is 4 pi g times the mass density. And this is, of course, that one what later will be then generalized to the Einstein equations. But here, we just have here that part. No? So here, this is then the same phi that has to be included here. And you see, these are coupled equations, right? So the rho and the phi are here, rho and phi are also here, and they determine the velocity and so on. So these are not really simple equations, I must say. So these are, as you see, 7 equations. So let us count them. No, so we have here, this is one equation for the rho, and so these are 3 equations for the 3 components of V, and this is one equation, and this is also one equation, 3, 4, 5, 6, and we also have then the equation of state, which also gives here one equation. And we have 7 variables. So these are the variables rho, V, S, phi, and p. No? So these are 1 plus 3 plus 1 plus 1 plus 1. So these are 7 variables. So that looks good. No? We have 7 equations for 7 variables. So except for some, of course, special cases where you have degeneracies, I mean, you know the theory of differential equations, but except for this, we can expect a unique solution, no? Given a nice boundary for initial value formulation. So these are in general complicated nonlinear equations. And if you want to solve them in general, there's no other way than to go to a good computer and solving this numerically. And this is, of course, a special field in physics, hydrodynamics or fluid dynamics, and which has widespread applications, for aerodynamics and for other. We are not interested in this. We are interested here in cosmology, and we are interested in the case where these correspond to very small perturbations of a homogeneous function. And there we can do a lot of things analytically, fortunately. So here we are only interested in small perturbations around a homogeneous and isotropic background. And so this is what leads to linear perturbation theory. And you know from observations from the cosmic microwave background anisotropies that these perturbations initially were very small, the order of 10 to minus 5. This is why in the context of the early universe this is fully sufficient and very good. Of course later, when these perturbations grow and galaxies form, this breaks down and we really have to do numerics. But this is not the subject of this course. No? This is what you learn in astrophysics lecture courses, the details of structure formation. So we are really about the early development of fluctuations. And this is why we can here, for the rest of the lecture course, really restrict ourselves to linear perturbation theory. Now, of course, this is the question we want to answer. how do these perturbations that initially are small grow in an expanding universe. But before we do that, we go to a static universe. Actually, that is the real Newtonian picture, because in Newton's theory, we assume, or in Newtonian time, that the universe is static. And this was also held in the 19th century, actually, until in the context of relativity, expanding universes were described. So we will first do the static case, and then we will do the expanding case in the Newtonian theory, which is not really historic because it was of no interest in the Newtonian days, but it will help us to understand the relativistic case. So let us first go to the static case, and this is in the literature also known as Jeans theory. So this is the theory for a static universe. And this is named after a British physicist and astronomer Sir James Jeans, who lived from 1877 to 1946, and who made important contributions to astrophysics, but also to standard physics. For example, you certainly know the Rayleigh-Jeans law in thermodynamics, which is the approximation to the Planck law. That's the same Jeans. Now, you could say, well, we just take rho equals constant, but rho equals constant, if you convince yourself, is not the solution of these equations. So this means that perturbations, once they are there, they change in time. And actually, they will grow in time. So rho equals constant is not a solution of the above equations. And in fact, because gravity is attractive, once they are there, they will further condensate and grow. So it's not surprising that perturbations grow in time. Now we make the following ansatz. So we write, the rho and also the other function of x and t. These are the functions that enter these equations. As a constant, which will serve as the background. We call this the rho naught, which is not dependent on x. Well, here also not dependent on t, because we are really in a static case. But later we will have here a function of t, which is the expanding background. But here it's just a constant plus the rho of x and t, and the absolute value of these is much smaller than rho naught, and also other quantities, of course, that will here emerge. Then the velocity field v of x and t is v naught plus delta v of x and t. But this v naught of the background we set to 0 because we assume a homogeneous background. So if we had a velocity field of the background, it would distinguish a direction. It would no longer be homogeneous. So here this is set to 0 because we have a homogeneous background. And okay, let us go here. So we have the Newtonian potential that we also disturb, of course. And the same holds for the entropy density. And also the pressure, which is a function of rho and s. Of course, we also have a perturbation, but we can relate this to the perturbations of phi of rho and s. So we have for the pressure P of x and t is P of rho naught plus delta rho naught s naught plus delta s. Sorry, that's here, which is given as dp over d rho at a constant s times delta rho. I mean, because these are small, so that's the first order expansion, plus dp over ds at constant rho times ds. So these coefficients, they get a particular name. So that here is known as the speed of sound squared, as you perhaps know from your earlier classes, that dp over d rho, which is a velocity squared, and actually this is how sound is how pressure perturbations propagate. So that's what we call speed of sound squared, and this here we call sigma here dp over ds. So so that's cs is the sound speed. Right. So let us have a brief look at the dimensions. So the dimension of rho, which is a mass density, is mass over length cubed. So dimension of rho is mass over length cube. That's what we have in Newtonian theory. And if you compare this with the dimension of the pressure, you find that it's dimension of the pressure over a speed squared. So if you take for this as a reference for the breakdown of the non-relativistic limited speed of light squared, which of course is in Newtonian theory not relevant, but viewed from the perspective of the relativistic theory, we can insert this here. So we assume here in the non-relativistic limit or approximation that p is much smaller than rho times c squared. Also we set cs and delta v much smaller than the speed of light, right? Otherwise the Newtonian approximation breaks down. So if we insert then rho is rho naught plus delta rho into these equations here, these hydrodynamic equations, and after some lengthy but straightforward manipulations that you find in the reference, we can derive an equation for the delta rho. Yeah, and I leave this as an exercise or leave it as a reading for you in the book. So insert into hydrodynamic equations, and so after some calculations you then find the following central equation on which the following is based. And that's the equation for delta rho. So we have a second derivative of delta rho, second time derivative, plus minus cs squared Laplace of delta rho, so the spatial derivatives, minus 4 pi g times rho naught times delta rho. And there's an inhomogeneity on the right hand side, which is the sigma, which is here this dp over ds times nabla squared Laplace delta s. So that will be, for the following discussion, the central equation from which we then infer how density fluctuations grow in the static universe and later in the expanding universe. So we have found this equation for the density perturbation rho. So this equation holds a Newtonian limit for a static universe, and it was derived from the hydrodynamic equations. So the following special cases are applied to this equation. So let us first discuss so-called adiabatic perturbations. They are defined by ds, entropy perturbations equals 0. That's the general definition of adiabatic. So this means that here the right-hand side is 0, and if the right-hand side is 0, you see all the coefficients here on the left-hand side, they are independent of x. And that these are just constants. So we can, with profit, perform a Fourier transform to find solutions. So we relate delta rho of x and t to the perturbations in momentum space. So that's then defines then d3x over, okay, there's this factor that we choose in this way, and then we have the delta rho k of t. So instead of the x here, you have then the k. Now the t is preserved, times e to the I k x. And it's very simple to insert this here and write down the equation for that in k space. And okay, here the first term is unchanged, just the second derivative of this here. So we have from star delta rho k double dot, and of course the Laplace goes to the minus k squared. So we have here plus k squared cs squared, minus this of course just stays, minus 4 pi g times rho naught delta rho k equal to 0. So the k without the arrow indicates the absolute value of the wave vector. So that's the equation we have to discuss right now, and you see that's a simple equation. It's an oscillator equation, but of course whether it's really an oscillator depends here on the sign of this, and that's really crucial. So the solutions that everyone can write down immediately are delta rho k proportional to e to the plus minus, and you have I, a function omega of k times t. Now this function is the square root of this here. So with omega of k is k squared cs squared minus 4 pi g o naught and the square root. That's what you have here. You see, this can also become imaginary if the second term, the gravity term, dominates. So there's a critical value, and the critical value is of course this when this is 0 here. So there's a critical angular frequency, omega at a particular value of k, which we call kj, and this stands for genes, for the James genes, whom we owe these investigations. And it's clear that k, well, I write it here separately, Kj is defined as twice square root of pi g rho naught over Cs. And you can relate, of course, the case to a wavelength. And this is called the Jeans length, a central quantity in astronomy. Jeans length. So lambda j is a 2 pi over kj. And yeah, from this you can write it as Cs times the square root of pi over g times rho naught. No? So this has dimension of velocity, it's a speed of sound, and this has a dimension of a time. So that's the famous Jeans length. So we have to naturally then distinguish between the cases where wavelengths are smaller than this and wavelengths are bigger than that. And the opposite holds for the wave numbers. So the first case, A, is lambda smaller than the Jeans length. So this means that this here is positive, the discriminant, and omega is real. And so you really have oscillating solutions. And these are then really the classical sound waves of that, which means that this gravity part here is irrelevant. Just if there were no gravity, then you just have your sound waves. So you have then oscillating solutions. And so these are the sound waves. So if I continue here, this means that I have then, so this is a continuation, so I have then here delta rho of x and t, then proportional, say, to the sine of omega t plus kx plus some initial angle phi. You can also calculate a phase velocity Cp, which is defined, as you know, as omega of k over k. And inserting omega k, you find here this is Cs times the square root of 1 minus kj over k squared. That's the phase velocity. So in the limit where lambda is much smaller than lambda Jeans, which means that k is much bigger than kj, then you have here that Cp goes to Cs, and which means that, I mean, actually kj is negligible, and kj negligible in a sense means that gravity is negligible. It would correspond to setting g equals 0. So if there were no gravity or gravity negligible, then k is 0 and the Jeans length is infinite. So this would then hold for all wavelengths. So this means gravity is negligible compared to pressure. But of course, for our situation and for astrophysics, kj is not 0, of course, and lambda t is not infinity. So there's a certain limit where up to which pressure dominates, but beyond that limit, gravity dominates. And this is absolutely crucial to understand structure in the universe. No? So that's then the condition B, so lambda is bigger than the Jeans length. And so this must mean actually that the second term here dominates. So you have here a minus, and the omega becomes imaginary. And you see an imaginary omega leads here to a real solution, exponentially expanding and decaying solutions. So we have here the omega imaginary, and you get then that the delta rho k is proportional to e to the plus minus absolute value of omega k times t. And you see we can distinguish here what in the literature is called the growing mode, the exponential expand, and the decaying mode. So that's a language that is used throughout, especially also in the inflationary universe. We talk about, you will see later, a growing mode and a decaying mode. So we have a growing mode, which is delta rho k is proportional to e to the plus absolute value omega t, and we have a decaying mode, so that delta rho of k is proportional e to the minus omega t. So in the limit k to 0, which means lambda is much bigger than lambda g, so it's just the opposite limit to that. We have, okay, omega, the absolute value of omega, which is imaginary, is just a square root of 4 pi g rho naught. And from that you get, if you insert that here, that delta rho k is proportional e to the plus or minus t over a critical time t. And that critical time t is of course defined from this expression. So the critical time t is defined the inverse, so it's 1 over square root of 4 pi g rho naught. It's also called the collapse time. This is where the index comes from, collapse time. For a region with an initial density rho naught, and so if the perturbation then grows, it becomes stronger and stronger, and you have a collapse, a gravitational collapse here. So these are, you see here, all these scales follow from essentially g times rho naught. You can write then here also lambda j as a 2 pi times cs times tc. 2 pi times speed of sound times collapse time. Now, how quick the perturbations grow, you can easily then estimate, because exponential growth is really quick growth. As you know, so if we have here, okay, delta rho over rho naught is say some delta rho initial over rho naught times e to the t over tc. So even if this were very small, so if you take this, for example, an amazingly small number, much smaller than what we have in cosmology, 10 to the minus 100, then and you calculate when this becomes of order 1, then, I mean, because of the exponential growth, this is very quickly achieved. So delta rho over rho naught is of order 1 after t roughly 230 times this critical time. So you see, you can start with whatever small you like, the things grow. So gravity causes the density perturbations to collapse. Okay, so far for the adiabatic perturbations ds equal to 0, let us briefly mention the so-called vector perturbations. As you will see, they are not so important, but I should include them for completeness. So this means vector perturbations that you only have delta v. Of course, in general, you have everything together, so these are the different cases. So if we have delta rho equals 0 and delta s equals 0, then this equation here you see is trivially fulfilled. So you have to go to the general perturbation equations that we had written down earlier on that blackboard. And without doing that here, so I don't present this here. So from the general equations, one gets that nabla dv is equal to 0, and also you get that from the Euler equations, dv over dt is equal to 0. So that is what you get, because most of the other terms, because of that, just vanish. So it's you can easily convince yourself. Now, from this, it's clear that dv is only a function of x, not of time. And from this equation here, if we make an ansatz, dv is some wk times e to the I kx, so some oscillating function. You can use whatever you like, but if you do that, then from this equation you see that these are orthogonal, right? So this and the k are orthogonal, because this gives you the k. So from this you get wk times k is equal to 0. So they are orthogonal to each other. The vector perturbation is orthogonal to so the direction of motion, the k, the wave number vector, which means that you only have two independent vector modes orthogonal to the direction of propagation, like when you discuss polarization, transversal polarization. So this means that we have two independent vector, so-called vector modes, orthogonal to k. So they describe what is called a shear motion, and they don't lead to a disturbance in the energy density. So they're actually, from this point of view, not so relevant then for the collapse. So the last thing here are then the entropy perturbations. Delta S is then unequal of 0, and then from this equation here you must also consider this inhomogeneity on the right hand side. Let me write this then down in the Fourier space, so using here again this transformation. So then we have here from equation star delta rho k double dot plus k squared cs squared minus 4 pi g rho naught delta rho k is minus sigma k squared delta s k. So that's now a new term. compared to earlier. It's an inhomogeneity, and inhomogeneity in the sense of the differential equation. So that's a homogeneous equation, and then that's inhomogeneity. And you know from the general theory that the general solution is a special solution of these inhomogeneous equations plus the general solution of the homogeneous one. The homogeneous one we have already discussed. This is this one with the oscillating or exponential solution, but we now also have a particular solution here that. So we have here the general solution. Is a special solution of this equation plus the general solution of the homogeneous equation. Now the homogeneous equation is for delta Sk equals 0, which we already have at our disposal. Now let me only here write down the solution for time independent delta S of k. Of course, if this depends on time, then yeah, it depends on the exact function. I mean, what solution you have, right? But if this is just a constant, then you can directly solve it. So, for example, t independent Sk. Then there's a special special solution with where this term is absent. So it's actually a time-independent solution for the density. So rho depends only on x. Well, that's not here. That's the rho k, but in position space. And so we have here delta rho k. Then you just then divide this through. Is a minus sigma k squared delta S k over k squared cs squared minus 4 pi g rho naught, which you can also write as minus sigma k squared delta sk over cs squared times k squared minus k genes squared. And so that's the entropy perturbation, the energy density perturbation that comes from entropy perturbations. Now for k to infinity, which means that lambda going to 0, of course this means gravity is unimportant. Then we have here, then this is just absent here, the kj, and we have here that delta rho k goes to minus sigma over cs squared times delta over sk. Just a final word on the pressure perturbations. The pressure perturbation you get from the equation of state. So we had from what we had previously, cs squared delta rho k plus sigma times delta sk, and if you have this here, okay, that's a general expression, but in this limit, so that we call this double star, it's just going to 0 here. So actually in that limit here, where gravity is unimportant, the two terms compensate each other and there's no pressure perturbation. So that's really particular for this entropy perturbation. Now it's clear that for structure formation, the exponentially decreasing part, the decaying mode, is not important. So what is important is, the growing part, because this makes the density perturbation stronger and stronger and stronger. From very small then to 1 and beyond, not to the nonlinear regime. What we are eventually interested in is the expanding universe. So that finishes the part on the Newtonian static universe. So next time we first start with the expanding universe in Newtonian context, and from this we can then proceed to the real case, which is using Einstein equations and general relativity. So far for today, so thank you for listening, and until next time.